Okay, welcome to the second part of the video series on functions as series. We're going to dive in to the same idea of geometric series and build our way from there. We last studied the finite geometric series formula, derived this, and we saw how this actually derived the infinite geometric series formula, knowing that this disappears because when r is less than 1, anything less than 1 to a larger and larger power, especially as it becomes infinite, this will become 0. And so that's going to be one of the premises of what we're going for, is we're always looking for that r value to be less than 1 moving forward. So let's keep that in mind with each example moving forward. Three common examples here to demonstrate some of the common notations. We have here the expanded form with the ... notation. That is a starting term of 1, which goes here in the formula, and then a common ratio of 1/3, which goes here in the formula, because that's our a over 1 minus r. And again, because r is less than 1, we get a nice crisp answer as a convergence. Similarly, you'll get summation notation. And in this, the number one thing you want to note is the starting index. Always plug in that starting index value of 0 and see what your first term is going to be. So when I is 0, you get an output of 2. And then each iteration after that is going to have a common ratio of r equal to 2/5. And because 2/5 is less than 1, you get a nice output of 10/3. Another common notation is to write out in terms. So we typically do like the first term, second term, third term, the ... and then the nth term. This is called the general term. And then you take the limit as the number of terms approach infinity. And again, this is geometric with a starting term of 5, a common ratio of now -3/4. And you'll see that this negative in the r is what indicates to us that we'll have an alternating sign in our series. And you'll see this in our future examples as well. So jumping forward, what this reveals to us now is actually a very exciting development, that now we can represent even functions as a series. And we're going to call these power series moving forward. And why we can do that here is, well, this is obviously a geometric series by nature. It starts with 1, and we're adding x and then x squared ... So each time we're multiplying by the same x value. So in this case, the x is our common ratio, and the 1 is our starting value. So we have here a function of the form a over 1 minus r, and we know that a over 1 minus r is the sum of a geometric series. So I now have a representation of a function through a power series. And we do need to keep in mind, though, that this representation is only equal when the value of x is less than 1, and that's absolute value of. So this is going to give us something called the interval of convergence. And it's not necessarily very clear as to what that means for right now. Essentially what it means is if I plug in like 1/2, then I will get the same output as if I plug 1/2 here. So if x is 1/2, these two things are equal. So what does it actually mean on a scale of an interval? Because we're talking about continuity at that point. So I have a Desmos animation built up so we can show what this looks like. And currently I'm showing the function of 1 over 1 minus x. And here you'll see I have a series listed out of the partial fractions. So this is a first partial fraction, a second partial fraction, third partial fraction, fourth partial fraction. By saying that partial fraction sentence, you're saying, give me the 4-term approximation of this function. That would be what a fourth partial sum is. So what happens as we begin getting closer and closer to the 4 or the function term? So you'll notice that as I'm clicking through these different graphs, each graph is becoming closer and closer to the red curve. In other words, the more of the terms that I use, the closer to my function I get. And it's becoming a bit monotonous to type in like x to the fourth, x to the fifth, x to the sixth, ... So instead, we use the convenient summation notation. We just say, let's add all the powers of x from 1 to capital N, and capital N is going to go from 1 to 25. So we can quickly on a slider see what happens as I add more and more partial fractions here. So now this is the fifth partial fraction, 6th, 7th, ... And as we see, the more terms I use, the closer my series, my power series, becomes to approximating my function. Now what's really cool about that is it's only true to make that statement on a certain interval. Now here you'll see that anything between -1 and 1, it seems that my power series is a very good approximation for my function. If I step outside that interval, let's say right here at like -1.5, the function value at -1.5 is nowhere near the polynomial value or the power series value at -1.5. So we say at -1.5, these two things are divergent. But at 0.5, they are convergent. They are essentially the same value. And we're only at 25 terms. If we want to say they are equal, we would have to go out to an infinite number of terms. So that's still a limiting problem. Now, the one point of concern that we need to move forward with, and we'll look at this in later videos, is what do we do with the endpoint? What do we do exactly at -1 and at 1? And because it's geometric, we know that we cannot include the endpoints. So that is a non-inclusive interval. And we'll talk more about endpoints in greater detail in later videos. So another example we have is this alternating geometric series where we have a -x² as r. And again, this is that situation where we have a -r, which is the alternating sign, and of course algebraically simplifies to this. So now what we're looking at is this function should be represented by this power series, and the more terms that we use, the more accurate we should become to this graph. And this is only going to be true when the r value, absolute value, is less than 1, which means that the -1 to 1 is our domain for convergence. And we should see that as we look here in the Desmos file. There's our 1/1 plus x² curve. And we have now a summation generation. Instead of typing out all the terms single-handedly, we'll just do it in a nice smooth algorithm here. So this is the first term, first two terms, first three terms, the fourth partial sum, fifth partial sum. And as we see, I add more and more partial sums here. The more that I add, the more accurate our power series will become to our function. And when are these two things seemingly accurate to each other? And that is only within the interval of convergence, which is from -1 to 1. Now again, do we include -1 or not include -1? And same for 1. That requires a little more analysis. Because we're using the geometric series, we are not going to include the interval or the endpoint. So that makes it easy when it's geometric. Okay, so moving forward, I have a few practice problems. Go ahead and pause the video here. On the next slide, I will produce the solutions. Okay, so hopefully you paused the video and you gave yourself some time to try these out. I think these aren't as hard as maybe the last challenging or the last problems were for the homework. So then a quick run through, we have f and g, where f is of the form a over 1 minus r. That's geometric, so we know that a is our first term and r is x². And the instructions say to write out the first 4 terms plus the general term, and then also the summation notation. And inside of this, we know that the r must be less than 1 absolute value, of course, which means the interval of convergence is from -1 to 1. Something to note is that I'm starting at k equals 1. You may, of course, have chosen to start at k equals 0, but if you did choose 0, then this is going to have to be 2k plus 1. So that's just an indices shift, and that's a critical skill for manipulating series. Okay, so moving on to the second example, this does not exactly look like our a over 1 minus r form. So we do some algebra manipulation, factor out the 4, and then change this plus to a minus a negative, and now this is a over 1 minus r. So we pull in our a as our first term, and then a negative 3/4 x as r. Write out the first 4 terms, plus the general term, and then also the summation notation. Now here I'm starting at k equals 0. It doesn't matter which one you start at. I gave you both just to do a reference point. Something that's important to note here, though, is that I could have chose to put the -1 inside with the 3/4 x. However, it is common notation to pull the -1 out to indicate to the reader that it is an alternating sign series. So just common practice, go ahead and do that for future reference. And then, of course, the r value should be less than 1. I know there's a negative missing there, but the absolute value of negative is positive, so we don't need to worry about the sign. And of course, then the answer breaks down to this. Lastly, for solution part 2, we see that this is geometric in nature. Every term is being multiplied by a negative x over 3, a negative x over 3, and a negative x over 3. So that's our r with the first term of x over 2. And this answer would be fine. This is just a prettier form if you want to simplify. And then again, this is also geometric. So you start out knowing that k is 0, you plug in 0, meaning this is going to be 1. Your first term is 2x squared divided by 1 minus x cubed, as x cubed is your r. Okay, thank you for watching. I'll be posting another video shortly, and I hope you enjoyed it. We'll be going much deeper down the rabbit hole in the next video. Thank you.